Okay. Hazza, do you mind getting the light? And then we'll start the next topic here. Now, this next topic is pretty straightforward. We're looking at probabilities, and we are representing them in a table. So, let's give an example to get started. Let's imagine X is the outcome from rolling a die, six-sided. You can represent all the possibilities in a table like this. So you can have X could have been 1, 2, 3, 4, 5, or 6. And the probabilities for each outcome would be 1 over 6, 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 and 1 over 6. Some things you notice about probabilities tables. All these numbers here must add up to 1. And all these numbers here represent the different outcomes. Like that. Okay? Now, I'll give you a second to write that down, and then I'll ask you to make me a probability table. Let's see if you can do it. So just write that one down as an example of a probability table, and then I'll give you one to see if you can draw it. Come on. Yeah.
So is it rolling a die or dice?
Die is the singular, dice is the plural.
Oh.
Yeah. So it's roll a die if it's 1, and roll a pair of dice for 2. Okay. Do you have that? Yeah? Yeah. You don't have it because you were on your phone when I was writing it.
Yes.
So the example I want you to try and draw is I want the probability table, and this time X represents flipping 2 coins, and you write down the result that you get. 2 coins, yeah, yeah. And you throw them up in the air at the same time, and they hit the table. Yeah, at the same time. Yeah, so you throw the 2 coins up, and you look at what you get on the table.
Is that possible? Oh, yeah, okay.
Yep, I'm trying to trick you. Yeah. What are those numbers? I can't quite see. And you have to move your hand. The numbers are wrong. Yeah. Yeah. It ain't 3. It ain't 6 either. Yeah, let's have a look. Right, the first one is heads, and there's a 1 in 4 chance of getting that. And if you don't, if you forgot how to calculate it, you draw your probability tree or Venn diagram or whatever. Okay. The next one we'll do, which is easy, is tails, tails. And likewise, there's a 1 in 4 chance for that.
Yes.
Tails and a tails. Therefore, the last one, heads, tails, which is the same as tails, heads. It has to be a half. It has to be because the total here must be 1. Yeah.
Ah, okay.
Is that alright, Ishpreet? Yes, is that okay? Yeah.
Teacher,
Yeah.
I didn't get the 1 over 2.
The total has to be 1. So what else? It couldn't be anything else.
And the 2.
The total has to be 1. So if this is a quarter and a quarter, then this has to be a half. There's no choice here. Yeah?
There's 4 outcomes.
Correct?
Yeah, I'm gonna write quarter and quarter for TH,
A quarter, and
2 other outcomes. Of course, there are 2.
yeah, but heads, tails, and tails, heads, they're the same.
It's not the same coin, it's tail. Not the same coin, it's tail. So maybe it's different.
I know, but we were talking about this yesterday. We can't distinguish between the 2 coins. I know there's 2 different coins, but if one of them is heads and one of them is tails, I can't tell which one is which. All I see on the table is a heads and a tails. Now, Hussein, if I change the question, if I said something like, I flip a €1 and a €2 coin at the same time, then yeah, the bigger coin, like, then you're right. Heads, tails, tails, heads. You can now tell a difference here because you can see the small coin and the big coin, you know. But I can't distinguish here. Okay. Can I scroll down?
Yes.
Yep. All right. Okay. Horse race. So we're looking at who will win the horse race. So obviously there's many different horses that are running, but we'll only look at even that's too many. We'll look at 3 and then we'll say other as the 4th one. So we'll say horse A, horse B, horse C, and then someone else wins instead. Okay. We'll say horse A is the most likely to win the race, and we'll give the probability of A being the winner as 0.4. And then we'll say B is likely to win the race, but it's not as likely as A to win the race, so we'll say it's 0.3. And then here is 0.2. And then the first question here, I'll call that X, but I think you already have it. My first question is, what is X?
1. 0.1.
0.1.
No.
Oops. And why is it 0.1? Hmm? It has to add up to 1, doesn't it? Yeah. Now, let's go with question B then. What is the probability that horse A or horse B wins the race? 0.7. Good. Okay. Good. Right. Next one. What is the probability that it's not B that wins the race? 0.7. Oh, that's funny. That's also 0.7. Just by coincidence here. D. What is the probability that it's not A, B, or C that wins the race? 0.1 down. Okay? Pretty straightforward so far? Yeah? Okay, let's see.
A second.
Okay. I know what I'll do. Yeah. Let's make it a bit more interesting. E now. Oh, it's changed colour. That must mean it's really hard. What is the probability that B wins, given that A falls? So as you're watching the race,
What's it?
A falls.
Falls down.
And the horse trips and falls and dies.
Aw.
Well, we won't say dies, but we'll just say falls and is out of the race. Okay. So what's the probability that B wins?
0.5.
Is it? Yeah. It looks like 0.5, doesn't it? Yeah.
Okay.
I have a question. B.
It's
Mm.
0.3 on top and then like 0.4 minus.
What? Not bad.
Uh,
What will happen?
I'll give you a minute to calculate it. We'll let the others catch up to us. Okay, don't be put off by A falls. Just you can think of that as A doesn't. Yeah, A loses. Yeah. Now, the reason I'm doing this one is I want to show you a different way to think about this. If I can scroll down. Well, actually, I can fit it here. So basically what has happened is as you're watching the race, you know that A is out of the question now. It's just simply not possible for A to win. So your choices of who's going to win has reduced by 1. It can only now be B,
C.
C,
CL.
or someone else. But the probabilities are not 0.4, 0.3, 0.2, or 0.1. Why are they not this anymore?
Because they have to sum up to 1.
They have to add up to 1. And they don't anymore. Why?
So the horse as well.
Because 1 is out, and you basically have missed out on 0.4 here. Okay? But what's nice about probabilities is they stay proportional. So what I mean by that is you can fix this table by multiplying everything by some number. I don't want to call it X, I'll call it Y. And make the probabilities add back up to 1. Do you get what I'm saying? It's like you've removed an option and then you've rescaled everything back to 1. Yeah. So what would the y need to be to get these numbers to add back up to 1? Well, 0.3y plus 0.2y plus 0.1y equals 0.5y, and you need that to equal
0.6y.
0.6y, and you need that to equal 1.
1.
So y would be 1 over 0.6. What's that? 1 point. 1 and 2/3. 1.67 roughly. Roughly. If you multiply all those numbers now by 1.67, let's see what we get. So if you don't mind doing that, please.
5.
So the first one now is 0.5.
Wait.
Is
I
it?
did a mistake. One is 0.5.
The first one is 0.5. Okay. And then the next one,
Is 0.3.
0.3. And then the last one has to be then 0.2, is it?
Yeah.
Yep.
Are you sure you did that right?
0.167.
Yeah, no, that's not right. Hang on. That doesn't seem right. You're multiplying these three numbers by 1.67.
Yeah, 22 is 3.3.
0.5, yeah, 0.2 is, what is it?
3.35.
Point
3.34.
3.34.
Wait,
No.
No.
0.334.
0.334, okay. And then the last one then is 0.16,
What?
167. Yeah. Okay. Yeah, okay, that's, well, slightly rounding error here, but they add up to 1 now. Well, they don't quite add up to 1 because we had to round off. They roughly add up to 1 then. Yeah. Now, yeah, it's slightly off because of rounding, because of the this guy here. Yeah. So this is a trick that you're allowed to do in probability when you start removing things, but everything else remains the same, you can bring everything back up to 1. And there's a verb for this in probability. It's good if you know it. It's called renormalize. It's a process you're allowed to do to bring the probabilities back to 1 if something gets excluded. Yeah? Okay, can we do one more of this? Just to practice another one? So,
Second.
So what's the answer?
Yeah.
what was it? There, 0.5. Now B has a chance of 0.5. Previously, what was its chance? 0.3 we said, wasn't it? 0.3. And now with A gone, it gets up to 0.5. Yeah? Okay, so the next part I'll ask you to do, just on this one, and then we'll do another example. So as you continue watching the race, now horse B falls. What is the probability C will win? Yeah. So you can renormalize again, yeah. Yeah. B is falling out now.
Okay.
So you're only looking at 2 possibilities.
Yes. 0 point
C or
else.
someone else.
Yes.
If you take out 0.5, what will your probabilities add up to, roughly speaking, now is only 0.5? You're only left with these 2. What should they add up to? 1. So how do we renormalize? We should multiply everything by 2. Okay? So that will become 0.667, and this one will be 0.333.
Why 2?
Well, these 2 add up to 0.5,
Yes.
and they should add up to 1.
Mm-hmm.
So what do you multiply 0.5 by to make it become 1? So what's the chance of C winning now? 0.667. Yeah? Now, it doesn't have to be,
1.33
what is?
C.
0.667.
Yes. 1.334.
What's 1.334?
When I times by 2.
When you times what by 2?
C.
What? Which? No, this is the answer. You're timing this one by 2, and you should get this.
Ah, okay.
All right. Did you write that down? Yeah. Let's see now. Right. Let me give you another one here. Oh yeah. So this last one here, else. I mean, there could be many, many horses in this group, right? Like, if there were 10 horses running, how many could be in this group here?
No.
At the very beginning, there were 10 horses running. How many's in the else group? 7. Yeah. So you're just saying that the chance that one of these 7 wins the race is 0.333. Okay? But of course, within these 7, you could maybe do another table, because they're not all going to be equally likely, I'd say. Yeah. Right, I'll give you another one here. Let's see. Have you done genetics yet?
No.
Not yet. You haven't done the dominant
Intro.
recessive.
No.
Not here.
Like,
Yeah.
It's the last chapter.
Oh, is it? All right.
Wow.
Are most of you?
after those.
Leave them alone.
Let's do it.
Right.
Let's do it.
How does it, why does it work? You could have something like 1 parent here and then one parent here, isn't it?
Yeah.
And then these can combine to make A.
Usually make a table.
Yeah, no, I'm just listing out.
Wow.
Hang on, I've lost track of what I'm doing. Let me start that again. A. It's like that, isn't it?
Yeah.
Yeah. So, event and probability. So, no, this one's kind of silly because if A is dominant, then it'll be all the 4 children will look the same. We'll have to make it a bit more interesting by making it a small A in each, isn't it?
Yes.
Yeah. So you could have that, or that, or that, or that. Okay.
2 are the same.
I know, yeah. So this is what I'm doing for my table here. What's
A
wrong?
small and A capital. Yeah, they're the same.
Which, these two?
Yeah.
Yeah, no, I know that.
Okay.
Yeah. So in both these cases, the trait appears, as in this case here, right? It's only in this one here where you don't have the trait. So I only care about 2 possibilities here. Either the child has the trait, or they don't have the trait. So what's the probability that they'll have the trait? Yeah, 3/4, and then here is 1/4. Okay, so you haven't done this yet, but you must have seen it before then. Yeah, this is kind of basic, very basic genetic stuff, isn't it? Yeah, okay. So that's that probability table there. Right. Yeah, no, I think that's okay. This is very simple stuff here. Yeah, very simple. And there's only 4 questions. Okay, so I'll let you get a start on these now. So, all 4, please. So, Carul, just to be clear, that's question 1, question 2, 3 and 4. Yeah.
I have a question.
And all parts in all questions. Yeah. Yeah.
How did we get it?
Oh, I added A and B.
5.
Oh. Did you write it down wrong? No, it's okay.
Good.